Right, let's continue our discussion about equations for AP Physics. So we're going to start with two-dimensional motion. Two-dimensional kinematics basically uses the equations of one-dimensional kinematics with a couple of exceptions. With two-dimensional kinematics, of course, we split everything into horizontal and vertical. And horizontally, we have constant velocity. Vertically, we have constant acceleration. And the constant velocity means there's d equals vt. That's our one and only equation. So we have d, v, and t. And vertically, because we're accelerating, v naught, v, a, dt. Most often, what we're given is information enough that we can solve for time and then use the time on the other part to solve for what we're looking for. So for example, most often we end up using the don't need v equation for vertical, which is d equals v naught t plus 1/2 a t squared. Vertical displacement, vertical starting velocity, vertical acceleration, where that vertical acceleration is caused by gravity, and so it's usually, we use 10 or 9.8 for the acceleration of gravity near the Earth's surface. So that's how we deal with two-dimensional kinematics. There are a couple of other equations that we deal with in two-dimensional kinematics. One is called the range equation, and the range equation is not very commonly used, but occasionally it's used. It is as such: range equals v naught squared times sine of 2 theta over g. Now, the range equation is only good if vertical displacement, I'll call that delta y, is 0. So if I have a projectile and it's launched from the ground, it's going to come back and hit the ground, I can use the range equation. The range is defined as this horizontal displacement right here. But remember, it's only good if we have 0 vertical displacement. If this is going to land on a roof, it doesn't work. If it's going to go off a cliff and go lower, it's not going to work. This will give us that horizontal range using that range equation. We also have in two-dimensional motion uniform circular motion. And uniform circular motion, or UCM, we have an object that's moving in a circular path at constant speed. Says that the acceleration towards the center, or a centripetal acceleration, is equal to the speed squared divided by the radius. So acceleration equals v squared over r. Now, this can also be written as omega squared times r, where omega is the angular velocity. So either one of these will give us the centripetal acceleration. Now, often we can see a situation where we can combine this with, if it's a uniform circular motion, and that means that the speed is constant, then the speed is equal to distance over time. And the distance around a circle is 2 pi r, and the time it takes for one complete circle is the period. So if I take speed equals 2 pi r over period, that's just distance over time, and I combine that into this equation v squared over r, I can see, for example, if I get v squared would be, square everything there, 4 pi squared r squared over t squared, and now if I do v squared over r, I get 4 pi squared r, because that one of the r's cancels, over t squared. So my centripetal acceleration is v squared over r, or same thing as 4 pi squared r over t squared. And those are the equations of two-dimensional motion. Now there's another two-dimensional that sometimes we deal with called relative motion. These are the types of problems where you have a boat crossing a stream and the stream is flowing, and this is just a vector addition problem. So if I have, for example, the velocity of the boat in the water plus the velocity of the water with respect to the shore equals the velocity of the boat with respect to the shore. So, for example, if I've got a river here and the river current is flowing down this way, this would be my velocity of the boat in the water. The water is going this way, so that's my velocity of the water to shore, and then the resultant vector here, where I actually end up traveling like this, my vector addition here, velocity of boat shore. Now those are vectors, so as I deal with them as vectors, I'm going to do it because it's two-dimensional. I do the same thing that I did with projectile motion. I split up a horizontal and a vertical, only in this case I've got constant velocity for both horizontal and vertical, but I can run this equation for the horizontal components and I can run this equation for the vertical components. So those are my equations of two-dimensional kinematics. this brings us to equations of Newton's laws. So let's look at Newton's laws. Newton's laws basically is dealing with forces and the result of forces, which are accelerations. So Newton's laws, we have a couple of equations. The sum of the force vectors, or the net force, is equal to mass times acceleration. So we could say, we could split that into horizontal and vertical. Sum of the Fx equals m times ax. Sum of the Fy equals m times ay. Okay, just like we can do with anything. We also know that the force of gravity, also known as weight, in a constant gravitational field is equal to the mass times little g. Little g here is the acceleration of gravity, or sometimes is referred to as the gravitational field, or gravitational field strength. Numerically, they're the same. The gravitational field and the acceleration of gravity are numerically the same. For the Earth, it's 9.8. Often we use 10 just to make the math a little bit easier. Generally, acceleration, we would list it as meters per second squared, so 10 meters per second squared. Gravitational field is often expressed in terms of newtons per kilogram. And dimensionally, newtons per kilogram is the same as meters per second squared. So force of gravity equals m times g. We also have Newton's law of universal gravitation, that the force of gravity is equal to big G times mass 1 times mass 2 over r squared, r being the distance between the centers of the two objects. So we've got this force of gravity here. And if we set these two equal to each other, since they're both equal to the force of gravity, say I've got, a stapler and the Earth. The weight of the stapler is m times g, and the weight of the stapler is big G times mass of the stapler, mass of the Earth, over r squared. So notice that the mass of the stapler is going to cancel out, leave giving me just this expression right here. I'm going to use a capital R here, because if we're something near the surface of a planet, the distance between centers is essentially the radius of the planet. So this equation right here is an equation for the acceleration of gravity at the surface of a planet. It's just big G, mass of the planet, over radius of the planet squared. We also have, in Newton's laws and with forces, we learned about the force of friction. And there are two kinds of friction. There's static friction, and there's kinetic friction. Static friction is friction on objects where the surfaces are not moving relative to each other. In kinetic friction, the two surfaces are moving relative to each other. So for static friction, Fs is less than or equal to mu s times the normal force. For kinetic friction, Fk, it is equal to mu k times the normal force. So static friction, interesting thing there, it will match an opposing force up to its maximum value of mu times the normal force. But you can't use mu times the normal to calculate how much friction is present. You have to use something like the net force equals mass times acceleration, or something like that. Or, left equals right, up equals down if the acceleration is 0. You can use balanced force equations as well. So that's friction. We also have the spring force equation, also known as Hooke's law, which says that the spring force is equal to kx. Now that's the magnitude of the force. In vector form, if we look at the vector of the spring force, it will equal negative kx, because it is always, the spring force is always opposite the direction of the displacement of the spring. So in vector form, it looks like spring force equals negative kx. Then we also have, in forces, we have Kepler's laws. And basically, without going into too much deriving, t squared over r cubed equals a constant. If we have any two objects that orbit the same central body, then the ratio of period squared to orbital radius cubed will be the same. In other words, I can set this up and say, Earth and Mars, for example. The period of Earth squared over Earth's orbital radius cubed equals the period of Mars squared over the orbital radius of Mars cubed, like so. And then I can solve it that way. There's another variant of this equation, which comes from taking Newton's law of gravitation and setting it equal to mv squared over r, and then you solve it out. So what you end up with there, it actually looks like this. T squared over r cubed equals 4 pi squared over gm. And the m here is the mass of the central body. And so you can see why the ratio t period squared to radius cubed is equal to a constant. Because you've got constant, 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 and the mass of the central body is a constant for objects that orbit that body. So those are expressions of Kepler's laws. We also have, as we mentioned briefly, when we have net force equals ma, if we're talking about circular motion, then we could say that the acceleration is v squared over r, and so the net force can equal m times v squared over r, or mv squared over r for circular motion. Those are some equations of Newton's laws.